Okay, Algebra 2, as we move into Chapter 14 here, kind of a tough chapter, we're going to start dealing with something called trigonometric identities. And we're starting to move towards, in Chapter 14, the big thing that we've done in almost every chapter this year, which is eventually solving equations. These ones are going to be with trigonometry. But to do that, we've kind of got to build up a toolbox, some methods and some skills that we're going to need to have mastered in order to be able to solve those equations there. Anywho, we start off with some trigonometric identities, mathematical statements that we know are true, and we'll talk about why as we go through here. So the first thing we're going to do is break these up. I've never had a great way of organizing these, so I'm just calling this the three groups of trig identities. These aren't the only ones, but they're the ones we're going to need for this chapter here in Algebra 2. So the first group right here is what I'm calling the reciprocal identities, and these ones you should know already. We should have seen these coming out of the end of Chapter 13. Cosecant of theta, everybody, the definition of that is that cosecant is the reciprocal of, or 1 over, that would be the sine of theta. Going right along with that now, secant of theta is the reciprocal of cosine of theta. Notice, guys, I'm keeping the theta there every step along the way. The angle doesn't change. And cotangent of theta is defined as the reciprocal of, or 1 over the tangent of theta. So those are the three definitions of the reciprocal trig functions. While we're at it, though, I think it probably wouldn't be a bad idea just to go one step further. If we remember back from Chapter 13, we defined the sine of an angle. Remember from geometry, you guys knew sine is opposite leg over hypotenuse, but in the XYR world that we tried to get you guys used to in Chapter 13, sine was defined as the ratio of y divided by r. Cosecant, then, is the reciprocal of that, which is going to be y over x for any point that's located on a circle, whether it's a unit circle or some other size. Going right along with that, cosine was defined as, I said that right, and then I wrote that wrong, guys, sorry about that. Cosecant is going to be r over y, the reciprocal of this. I was looking ahead. Cosine is x over r, so when we reciprocate that, secant becomes r over x. And tangent, right here, we defined as y over x. So cotangent is the reciprocal of that, which is going to be x over y. Okay, guys, so those are some different definitions now of the reciprocal identities. Let's talk about these ones right over here. Now, you guys already obviously know what tangent and cotangent are, but something new right here that's going to help us in this chapter. Tangent of theta could be rewritten as the sine of whatever theta is divided by the cosine of that same angle. And that's what I want to talk to you guys about real quick and discuss why that is. We won't do this with every one of these identities, but real quick off to the side, here's what we just wrote down, that the tangent of an angle is equal to the sine of an angle theta divided by the cosine of the same angle theta. Let's see if we can explore that and talk about why that is. Given those XYR definitions that we just talked about, sine, we said, is always going to be the value of y divided by r. Cosine, on the other hand, is always going to be x over r. And how do you divide one fraction by another? You leave the first fraction alone, y over r, and multiply it by the divisor here. So this gets multiplied now by r over x. We're multiplying by the reciprocal there. The r's are going to cancel each other out, which is going to leave you now with y over x, which I'm hoping you recognize is the definition of tangent of theta. So that kind of supports the idea that we just talked about right there. Tangent of theta could be rewritten as sine of theta over cosine of theta. Cotangent of theta, though, is just going to be the reciprocal of what we just wrote down. So cotangent of theta could be rewritten as the cosine of theta divided by the sine of theta. All right, guys, so there's the first 5 identities here that we have to have written down. Let's move on now to the second group right here, which are called the Pythagorean identities. And this one I want to take just a little bit more time with to discuss where these ideas come from. This diagram that I have written in the upper right-hand corner, I'm hoping looks familiar to you guys. It's part of, you don't need to draw the whole thing, but a whole circle diagram. And any point right there, guys, if it had the coordinates x comma y, we can make a triangle here by drawing our radius and our altitude to the x-axis. Now, whatever your x-coordinate at this point is, that's how far you have to move right from the origin. And whatever your y-coordinate is, that's how far you need to move up from the x-axis to get to this point right here. So again, I'm hoping this diagram looks familiar. It's a right triangle with legs of x and y, and a hypotenuse then that's equal to the radius of your circle. So with that in mind, let me get rid of all of this right here. And you probably talked about this at some point within chapter 13. Every triangle at any point that you draw here can be labeled this way. And since every one of these is a right triangle, the Pythagorean theorem ties together the lengths of the three sides. Leg squared plus the other leg squared has to equal your hypotenuse, r squared. So x squared plus y squared equals r squared. It is true for any point that we choose on the unit circle, whether it was here or here or here or here. And I did just say any point on the unit circle. It actually works on non-unit circles as well. R doesn't have to be 1 for this relationship to hold true. So now what we're going to do, guys, hoping we're understanding that statement I just wrote in purple, I'm going to divide all three terms of this equation here by r squared. And that's going to give us our first Pythagorean trigonometric identity. What we have right here, guys, is x squared divided by r squared. And if we go back to way back to something we learned this year, this is actually x over r quantity squared. And what is the definition of x over r? That one we learned a while ago is the cosine of an angle theta that gets squared. So this term right here, when we divide it by r squared, becomes cosine of theta. And guys, the way we write this, you're going to see this throughout the rest of the year. And if you take pre-calc next year, a whole bunch more. The way we write cosine of theta squared is we put a little square here. And we would read that as cosine squared of theta, but it actually means this. Take the cosine of theta first, then square that result. Okay, back to my purple statement now. I've got a plus sign right here. And now look at what we have, guys. Y squared over r squared. Now again, you can just make that y over r quantity squared, and then y over r is the definition of sine of theta squared. So this is cosine squared of theta plus the sine squared of theta equals, and here's the easy part, guys, this right side of the equation, r squared over r squared, just becomes a 1. So we end up with this statement right here, guys, cosine squared of theta plus sine squared of theta is equal to 1. And that is the first, the most important, and the most basic of all the Pythagorean identities. If you wanted to play with that idea just a little bit to verify that and make sure that's right, let me take a look at this calculator that I have here, guys. Now, I'm in radians, but it actually doesn't matter if you're in radians or degrees here. I'm going to, now you guys have to do this with me, you got to put a parenthesis first, and then I'm going to do the cosine, and you can put any angle you want right here. Again, it doesn't matter if you're in radians or degrees, just pick a random number. I'm going to do 11, sure. So cosine of 11, close the angle, close the cosine, and let's square all of that. So that's cosine squared of 11. For me, it's 11 radians. You might be in degrees, so it's 11 degrees. It doesn't matter. And then plus, parenthesis, now we're going to do a sine, and you have to type in the same angle here that you used just a second ago. Close the angle, close the sine, and let's square that. And the identity we just wrote down said cosine squared of any angle plus sine squared of the same angle should always equal 1. So when I hit enter, boom, there you go. We got 1 for the result there. And hopefully you got the same thing, whether you were in degrees or radians, and whatever number you picked. So hopefully that kind of teaches you guys that, okay, that idea actually makes some sense. Now, the second and the third of these guys right here, guys, are going to come from taking each of these three parts of this particular identity and dividing them all by, doesn't matter what order you do this, I'm going to divide them all by cosine squared of theta. As long as you're dividing by the same thing in all three cases, that's fine. Now, what does this first term become? Cosine squared of theta divided by cosine squared of theta. Anything divided by itself is 1. Plus, how about this second term right here, guys? Sine divided by cosine. We learned this just a second ago. Sine over cosine right here, guys, is the definition of tangent, or a definition of tangent, I should say. So that second term now is going to become tangent squared of theta equals, And now on the right side, 1 over cosine, that's the definition of secant. So this right side becomes secant squared of theta. And there is your second Pythagorean trigonometric identity. And for the third one, I'm going to go back to what we had here just a second ago, guys, but now instead of dividing everything by cosine squared, we're going to mix it up a little bit and divide everything by sine squared of theta. So let's do that in all three parts here, and let's see what that one does for us, sine squared of theta. So this idea is going to take us down here to Pythagorean identity number 3. Cosine divided by sine, going back to where we were just a second ago, now we're looking here. Cosine over sine is another definition of cotangent. So this left term becomes the cotangent squared of theta. Plus, how about this middle term right here, guys? Sine squared divided by sine squared is going to get us 1. And on the right side, 1 over sine squared, that's the definition of cosecant squared of theta. So those are your 3 Pythagorean trigonometric identities. Now I do have to warn you guys, there's 3 that you see written right here. Each one of them actually has 3 different variations. So in a way of speaking, it actually could seem like there's 9. Let me show you what I mean. The first one we wrote down, the most common, was this. Cosine squared of theta plus sine squared of theta is equal to 1. But it might benefit us in some cases that we're going to see a little bit later if we solve that equation for a different term. Like for example, if I wanted to get cosine squared of theta by itself, I could subtract the sine squared of theta from both sides of the equation, just using some basic properties of algebra, and what I would be left with then is the second variation. So this was like identity 1, and I'll call that A. Here's 1B right underneath that, guys. We would have cosine squared of theta. These next 2 terms, here and here, would cancel each other out, and the right side is simply 1 minus the sine squared of theta. Nothing you can do to simplify that. And for the third variant right here, what if we wanted to get sine squared by itself? We could bring this cosine squared over to the right side, and we would now end up with sine squared of theta is equal to 1 minus cosine squared of theta. So these are 3 different variants. We'll call them A, B, and C. 3 different variants all on the same theme here of Pythagorean identity number 1, cosine squared plus sine squared is equal to 1. And you can do the same thing here with identity number 2 and the same thing here with identity number 3. So I'm not sure that it's necessary for you to write all of those down, but I think having at least the idea in mind that the second and, well, actually all 3 of those Pythagorean identities could be rewritten and expressed differently might benefit you when it's time to get into the second group of problems here of simplifying trig expressions. I'm going to cut this video off right here, and then part 2 is going to pick it up at this next spot here, guys.